There's another important principle in math that we need to understand so that we can be successful using the elimination method for solving a system, and it's this. This equation is true because the left side equals the right side. If we were to add 7 to this side and add 7 to this side, again, both sides stay equal. If instead we say, oh, you know what, I want to multiply this side by 2, well, as long as we multiply this side by 2, also both sides will stay equal if we check that out. That's important for this. When we're trying to solve this system of equations, since this left side equals that right side, if we add 2 to the 16 and we get 18, then this left side should equal 2. We could add it to the first equation, and that would also keep both sides equal. Now, a nice thing happens when we add the equations together. 2x plus negative 2x is 0x. It goes bye-bye. 0x is worth nothing, so we eliminated the variable. Well, what's nice about that is, look what's left. 3y plus 6y is 9y. Now, just like in the substitution method, we have one equation left with only one variable in it, so we're going to be able to figure out the value of y. Divide both sides by 9, we get that y is equal to 2. What do we know so far? So far we know that the y coordinate of the one-ordered pair solution for these two equations has a 2 in it. And then the last thing we do is we say, oh yeah, now that we know y is 2, go back up to either equation, and where you see the y, you can replace it with 2. So 2x plus 3 times 2, that's 6, equals 16. So we have 2x plus 6 is equal to 16. Subtract 6 from both sides. We get that 2x is equal to 10. Divide by 2, you get that x is 5. There you go. That's your ordered pair solution to that system of equations. Alright, now we get here. Now remember before, if we ever have opposite coefficients, when we add the left sides together and the right sides together, in other words, add the two equations together, we will eliminate that variable. We don't have that situation here, at least not yet. But we go back to the notion that you have the right to multiply the left and the right side of an equation by a number, and it keeps both sides equal. Since there's a negative 4y in this equation, if we could create a 4y in that equation, then we'd have this situation where we can add together and a variable is eliminated. So our goal, get a 4y right there, but we have to use good math to do it. The good math we'll use is to say, hey, I'm going to multiply the left side of this equation by 2, and as long as I multiply the right side by the same amount, I keep both sides equal. Alright, let's write this new equation then. After we multiply both sides by 2, we get 6x plus 4y is equal to 28. Now let's bring this equation down and just leave it the way it was. That's 5x minus 4y is equal to negative 6. Now we have a system of equations where a variable is ready to be eliminated. It's kind of like playing a video game. We're going to eliminate the y's. It's awesome. So now what we can do is add the two equations together. What we're really doing when we're adding the two equations together is, since this left side equals this right side, we're literally adding negative 6 to 28 and getting 22. And we're literally adding this left side, which must be negative 6, to this side also. Well, here we go. 6x plus 5x, so that's 11x. 4y plus, negative 4y, that's 0. 0y, got eliminated. We are just left with one equation with one variable in it. If 11x equals 22, then it must be true that x is equal to 2. We now know the x-coordinate of our ordered pair solution to both equations. Why do we know that it's legit that 2 must work for both of them? Well, I'm glad you asked. The reason is both equations are influencing this outcome. We combine both equations to get this equation with only one variable in it. So since both equations are contributing information, we're preserving the relationship between x and y in both equations. That's why we know that 2 is the x-coordinate for the one and only ordered pair solution to both equations. Hey, once we know that x equals 2, pick either of these two equations and put 2 back in for x. Let's get blue. Let's put this guy back into this equation this time, the second one. So here's what we have. We have 5 times the known value of x must be 2, minus 4y is equal to negative 6. This is 10. 5 times 2 is 10. Let's take 10 away from the left side and 10 away from the right side. Getting messy, got to be careful. This is 0 minus 4y, so that's going to leave us with a negative 4y on the left side of the equation. And negative 6 minus 10 is a negative 16. So now, again, one equation with one variable. We divide both sides by negative 4. We get that y is positive 4, and bingo, there's our ordered pair solution to that system of equations. Now we get here, again, we want to create this scenario where we have opposite coefficients in front of a variable, because we know that when we add the two equations together, the left sides and the right sides, we eliminate the variable. Uh-oh, we got a lot of work to do here. We need opposite coefficients. We could try to create an opposite coefficient here and here, and you have to think, what number has both 2 and 5s as its factors? That would be 10. So we have a couple options. We could create a system where we have 10x in one equation and negative 10x in another, and then we'll be able to eliminate those. So let's do that. How do we get a 10x here and a negative 10x here? Well, we could multiply this left side of the equation by 5, and let's do the same thing on the right side. And we could multiply this equation by 2, because by negative 2, because negative 2 times 5x will give us the negative 10x, and then negative 2 times 4y is going to give us a negative 8y. And on the right side, we have to do the same thing, multiply by negative 2. That gives us a 22. Meanwhile, back in the first equation, we chose to multiply both sides by 5 because 5 times 2x would give us the 10x we want. 5 times this is going to be 15y, and that has to equal negative 15. Okay, so now what do we have? We now have a system of equations where we created opposite coefficients. So now, when we add these two equations together, this left side and this right side equals, so we add the same thing to both sides. When we add these guys up, those are eliminated. This gives us 0. This gives us 7y is equal to 7. Easy. Y must be 1. We now know that the y coordinate of our ordered pair solution is 1. And now we can put 1 back into any 4 of these equations up here. If we put a 1 back here, we get the 2x plus 3 times 1. So 2x plus 3 is equal to a negative 3. So if 2x plus 3 is equal to negative 3, let's solve that two-step equation. Let's take away 3 from both sides. We'll be left with 2x equals negative 6. Dividing by 2 leaves us with x is a negative 3. There is our ordered pair solution for this equation. Now let's do this a slightly different way. Let me go pick a new color. Let's do orange. Okay, let's not do orange. Let's do this green right here. So now let's do this. In this scenario, we tried to create opposite coefficients for the x. So to get a 10 and a negative 10, we multiplied by 5 and 2. Let's do it a different way. Let's pick on the y variable. 3 and 4 are both going to 12. So if we could create a 12y and a negative 12y in our two equations, we could eliminate the y. How do we end up creating a 12 and a negative 12? Well, we'd have to take this equation up here, and instead of multiplying by 5, we would now multiply by 4. Multiply both sides of the equation by 4. 4 times 2x is 8x. 4 times 3y is the 12y. And 4 times negative 3 is negative 12. Now we need a negative 12y here. We get a negative 12 here by multiplying by negative 3, not by negative 2. So we will multiply both sides by negative 3. Negative 3 times 5x is negative 15x. The negative 3 times the 4y gives us negative 12y, and negative 3 times negative 11 is a positive 33. So now we have another system of equations where we can eliminate the y, because we got the opposite coefficients there. So we are now ready to add these two equations together. This plus this is negative 7x. That's eliminated. This plus this is 0. I'd rather not see students go like that. I'd rather see them say this adds up to 0. That's why it goes bye-bye. And then this plus this is going to give us 21. So now if negative 7x equals 21, we divide both sides by negative 7, and lo and behold, x is negative 3. we are well on our way to getting the solution all over again where x is -3. We know that the x coordinate of our solution, our ordered pair, is -3. Now that we know that x is -3, we can take this value and put it back into any of the equations that we see up here. So we could go all the way back up here, and you'll see that once you put in a -3 right there, that you're going to end up getting the y value, oh sorry, -3 and for x, that the y value is going to come out to be 1 all over again. So at any rate, it doesn't matter which variable you eliminate. Just do good math, multiply both sides by the same number, create opposite coefficients for x or opposite for y, because then when you add the equations together, you are left with one equation with one unknown in it, and that's the key to solving systems.